A very good morning. Myself Sakshi Sanjay Patil, roll number 93 from Mechanical B Division. So today we are going to discuss about superconductor. So what is actually a superconductor? A superconductor is defined as a substance that offers no resistance to the electric current when it becomes colder than a critical temperature. They are different from ordinary conductors such as copper. Unlike regular conductors whose resistance gradually decreases, the superconductor's resistance drops to zero below a fixed temperature, which is known as the critical temperature. To become superconductor, most material must be in an incredibly low energy state, which is a very cold state. Presently, excessive energy must be used in the cooling process, making superconductors uneconomical and inefficient. Superconductivity. This phenomena was first discovered by H.K. Barnes in 1911 when he was trying to measure the electrical conductivity of metals at low temperature. Superconductivity is the ability of certain materials to conduct electric current with practically zero resistance. The capacity produces interesting and potentially useful effects. For a material to behave as a superconductor, low temperature are required. These materials also expel magnetic fields as they transition to the superconducting state. Some examples of superconductor include aluminum, magnesium diboride, niobium, and copper oxide.
Good morning friends, myself Sanika Pawar. I am from Mechanical B. My roll number is 101. Now we will see critical temperature. The temperature at which the transition from normal state to superconducting state takes place on cooling in the absence of magnetic field is called as critical temperature. Critical temperature is also known as transition temperature, or the temperature below which the electronical resistance disappears is called as critical temperature. It is different from different material. There are three properties of superconductor. First, zero resistance, second, Meissner effect, and third, critical magnetic field. Conductor in the zero resistance. A conductor in the form of ring is kept in external magnetic field. It is then pulled below DC so that resistance approach to zero and simultaneously external magnetic field is switched off. Due to electromagnetic induction, an induct current flow through it. This current will decreases. If resistance R is zero, this current will not decreases and will produce constant magnetic field so that the coil does not show any current. This provides that resistance is zero. Such current is flowing undisminishedly. It is used for the production of paramagnetic.
Hi everyone, myself Dipanshu Dinesh Routh, roll number 109 from Mechanical B Division. I am currently pursuing my first year BE in Maratha Vidya Prasarak College of Engineering, Nasik. I'm gonna explain you about Meissner effect. When a weak magnetic is applied to a superconducting specimen at a temperature below transition temperature T suffix C, the magnetic flux lines are expelled. This phenomena is called Meissner effect, as you can see it in the given below diagram. Coming to the next slide, when a conductor is placed in a magnetic field, the magnetic flux penetrates through it. Thus, expulsion of magnetic field as soon as the conductor becomes superconductor is known as Meissner's effect. Also, magnetic susceptibility for superconductor means it exhibits perfect diamagnetism. Thus, a superconducting beam will levitate about magnet is known as levitating or levitation effect. On the next slide, there is a graphical representation of critical magnetic field. You can see variation in critical magnetic field with the temperature at conducting state at normal state.
Hello friends, myself Saravansh Pote and I'm going to explain on the topic of types of superconductor. So based on the diamagnetic response, superconductor can be classified into two types. They are type 1 superconductors and type 2 superconductors. So talking about the type 1 superconductors, superconductors which one follow a complete Misner effect is called type 1 superconductors. They are also called as soft superconductors. So, when the magnetic field strength is gradually increased from its initial value, when the H is less than Sc, at Sc the diamagnetism is abruptly disappear and the transition from superconducting state to normal state is sharp as shown in figure. These superconductors are known as soft superconductors. The examples of type 1 superconductors are aluminum, zinc, tin, etc. Talking about the type 2 superconductors, superconductors which does not follow the complete Misner effect is called type 2 superconductors. They are also known as hard superconductors. In type 2 superconductors, the specimen is in pure superconducting state up to the field. When the field is increased beyond, the magnetic flux lines start penetrating. This specimen is in mixed state between, and above the specimen is in normal state. This means that the Misner effect is incomplete in the region between and. This region is known as vortex region. The superconductors are known as hard superconductors. Examples of such superconductors are ZR and B. So now, in one shot, to differentiate between type 1 superconductors and type 2 superconductors, the first point is as soon as Sc is reached, resistance returns to its form, while in type 2 superconductors, the transition is gradual. In type 1 superconductors, Misner's effect fails and gets lost completely, while in type 2 superconductors, some surface supercurrent may flow. In type 1 superconductors, paramagnetic if moment is equal to 0, while in type 2 superconductors, vortex state is observed. In type 1 superconductors, external magnetic field is equal to internal magnetic field, while in type 2 superconductors, Misner effect is incomplete. So the last point, in type 1 superconductors, practical applications are less, while in type 2 superconductor, practical applications are more.
Hello friends, my name is Sachin Chandrakant Patil, mechanical branch, roll number 97. In today I am explain an isotopic effect. In superconductivity materials, the transmission temperature varies with the average isotopic mass of their consistence. The variation is founded to be a general from EC EC directly proportional to the mass minus acceleration, or Tc mass of upon minus acceleration is equal to constant. The value of A is approximately unit, and accordingly transmultiplication of isotopic effects evolution determination of a structural identification of intermediates and the incidence of a reaction mechanism. In this application, may chemists think only of hydrogen isotopic effect, since these effects are large and can be measured with easy. Example of application of superconductor include uh, medic medial devices, magnetic energy store system, motors, generators, transmitter, computer parts, and sensitive device for a measurement of magnetic field, electrical current, etc.